Okay, we're back discussing the last part of the types of things that we can be doing in terms of um, machine learning, and that's with looking at data clustering. And so we just finished up talking about the first type of clustering methods, and that's the K-method algorithm. And the next thing that we're talking about now, and we'll finish up with a variety of other methods here. So next is the fuzzy K-means clustering. So K-means uses hard partitioning and cluster determination. So it's either one or not. But what if there is no unambiguous data partition? Then we want to be using algorithms where the objects belong to many clusters with different members degree. And so we have this idea of soft partitioning. The difference for the K-mean clustering algorithms, each point xi belongs to one cluster, while in the fuzzy K-means clustering algorithms, data points are assigned to several clusters with different degrees of membership. So continuing on, for hierarchical clustering, partition-based methods do not assume the existence of substructures. What if there's a hierarchical data? Hierarchical clustering is more effective. In hierarchical clustering, clusters have subclusters, and subclusters have lower level subclusters, and so on. So we saw an illustration of that earlier in this lecture, the first part. So we can also have spectral cluster. Here we can represent data using a similarity graph. A vertex represents a data point xi. Vertices are connected if similar, SIL, between two data points, XI and XL, in positive or larger than certain threshold. An edge between the two vertices is weighted by SIL, and the goal is to find a partition where the edges between the different groups have small similarity weights, i.e. dissimilar points in different clusters, and without a group, there are high similarity weights, i.e. similar points within the cluster. And so here we're getting into graph theory a little bit with vertices and edges. So that's something that you could be thinking about. Next, we have self-organizing maps. While discovering patterns, the network undergoes changes in parameters by using self-organization. Self-organized learning uses frequent modifications of the synaptic weights in response to the input samples. Weight modifications are done with the help of learning rules. An overall global order emerges from the numerous local interactions, which can lead to form congruous behavior. We have the Gaussian mixture model, the GMM, is a set of Gaussian, i.e. normal distributions with means and covariances. So probabilistic clustering uses a statistical model called the mixture model. The clustering problem takes a set of instances and a pre-specified number of clusters with Gaussian distributions and work out each cluster mean and covariance and the population distribution between the clusters. The goal is to find the maximum likelihood mixture densities parameters via expectation maximization, EM. And then finishing up with Gaussian mixture models, and this is the last method we'll talk about in this, this chapter. Each distribution is given a probability, and particular instance would have a certain attributes if it were a member of that cluster. Every particular instant belongs to one of the clusters, and the approach is take a set of instances and a pre-specified number of clusters, work out the cluster's mean and covariance, and then populate and the population distribution between the clusters. All right, well, that's the end of that for clustering, and that is the last machine learning approach that we'll be covering, and the last chapter will be a summary, and I think it'll be an interesting way for us to bring together what we've talked about. Thank you.